There's quite a bit of terminology over the next few lessons, so please make sure that you do the reading as assigned for tonight. All right, but let's get started with some of the terminology you'll need to know. We'll start off with regards to forces. All right, the textbook definition of it are listed right over here, but the simple answer of it is that I just need you to think about the force. Can you reharness the energy in the effort you put into it? All right, so let's say that we have an elastic band over here and I stretch it out. Can I reharness the energy? Oh yeah, I can definitely reharness the energy I've stored into it. All right, so elastic bands are classified as a conservative force. So anything that which the energy can be reharnessed again is a conservative force. So elastic bands, springs, electric fields, and magnetic fields. For example, you have two north poles. If you squish them together with a force of, let's say, I don't know, 3 newtons, well, it's going to push back with a force of 3 newtons as well. All right, so because you can reharness that force again, or the effort there in pushing it in, then it's considered as a conservative force. On the other hand, with, let's say, for example, friction, I take this elastic band, I push it over here, you'll notice that I can't reharness that effort I put into it. All right, the energy is now gone, it's just converted into heat. So that's an example of a non-conservative force, friction. All right, so here's a cheat sheet for it in case if you want to look at the cheat sheet for what is defined as a conservative force and what isn't. And the reason I'm showing you this list over here is just to remind you that an electric force is considered as a conservative force. All right, so it can be used towards storing energy. And that's what you really need to know about this stuff over here. More definitions such as work. All right, now work is a scalar quantity, so there's no direction involved with it. All right, if I walk this way, then I've walked and burned off, I don't know, 3 joules of energy, or 3 calories of energy, if you really want to think about it that way. All right, and if I walk the opposite way, it doesn't become 3 joules of energy in the opposite direction, or negative 3 joules. It's just 3 joules was consumed. Okay. However, it doesn't exclude that the minus sign doesn't exist in the world of work. There is such thing as positive work and negative work. And let me just give you an example. All right, let's say I take, I don't know, this computer mouse over here. All right, I'm applying a force upwards. All right, so I'm applying effort into the system, into its environment. So I'm pushing this upwards. As I'm pushing it, it's moving in the direction I'm pushing it at. So I am doing positive work. If, on the other hand, this mouse is just too heavy for me to bear and I start to let it descend, well, now it's gravity acting on it, and my effort, even though I'm pushing it upwards, it's moving the opposite direction. So in this case over here, I'm doing negative work. All right. So as I'm pushing it upwards, I'm doing positive work. If I can't win, I'm letting gravity take over. I'm still trying to hold it upwards, but gravity's winning. Then I'm doing negative work. All right. So yeah, those are the textbook definitions of what positive work is and what negative work is. So you just have to really think about, what's happening to the object at that moment in time. All right. Are you applying force and the force is causing it to travel in the direction that you like? Or are you applying a force and unfortunately it's going in the direction against what you like? Because if it's going against the direction that you like, then your work will be defined as negative work. All right, and I think I use gravity as my example over here. And if you do the calculations for this, you'll see that it works out beautifully using our examples. All right, so if I take an object and I lift it upwards, the work will work out to a positive answer. Meanwhile, if I let the object drop from, I don't know, 10 kilometers down to 1 kilometer above the surface of the earth, and I sub everything into here, I'll notice that the negative work will be done. Okay, and other things I want to point out is that, for example, this formula over here, there's a minus sign over here that sometimes textbooks don't even write in, and you really got to think about whether if you need to use a plus sign or a minus sign. All right, because is it work that you've done in trying to store energy into the spring, or is it the energy that the spring is releasing into its environment? All right, where in this case over here, I think it's releasing the energy, and that's why it's a minus sign. Okay, I think. No, wait, if I squish a spring, then the spring does negative work. Oh yeah, so I'm storing energy, and it'll be negative. Yeah. All right, so you just have to watch out for your sign conventions and stick with that consistent nomenclature that you deal with, because some textbooks actually flip the signs around. All right, so if you're storing energy, it'll be positive. If it's releasing energy into the environment, then it's usually defined as a minus sign. Yeah, at least that's the usual convention for it. And friction always does negative work. All right. The good way of seeing that is that as I'm pushing it forwards, let's say this is the positive direction. I don't know, positive is forwards, but we find out that the force of friction is going the opposite direction. Well, it's a total of 180 degrees opposite of forwards. So if you sub in the 180 degrees into cosine of theta, well, the cosine of 180 gives you -1. All right, and you'll find out that friction, as a result, will always perform negative work. Okay, more terminology. Electric potential energy, and I think the hint is the word energy over here. All right, how much energy is either stored or released in a given situation. Okay, so if I apply a force onto an object and it causes the object to move in the same direction that I apply it at, or accelerate in that same direction, then I'm doing positive work. If for any reason it starts to decelerate, then I'm doing negative work, or moving the opposite direction, I'm doing negative work. All right, so what am I stating over here? Okay, I'm just creating a new formula over here. If we know that the electric force is equal to charge times E field, that we covered I think 2 lessons ago, and work by definition is force applied times distance, if we just simply sub this into here, then I get work is equal to Q times E field times distance. And whether if it's plus or minus, you really got to think about, well, what's happening? All right, am I storing energy, or is it releasing energy into the environment? Okay, because if I'm doing positive work, then it's moving the same direction I want it to go. Meanwhile, if it's decelerating, then it's going, or going in the opposite direction, then negative work is actually being done on the object. Okay, so you really got to think about, whether it's storing or releasing energy. All right, and as I mentioned from before, electric force is defined as a conservative force. And yeah, we'll just go through some textbook questions, as they are very good examples of solving these problems. Okay, so you can follow along with the textbook answer key, or you can follow along with what I'm going to share with you here. All right, so these are 2 different takes on the same exact question. Okay, so an electron enters from the left into a long uniform electric field that looks like this. All right, so I'll just draw a bunch of arrows just representing the electric field. So electric field is pointing towards the right. In your imagination, you can think about it as a positive charge here, and E fields will be moving to the right. Although in truth, with that positive charge, you're going to have a radial E field, but I just hope that you just get the idea. Right? In general, it's something that's positive over here, and that's why the E fields are moving this way. And yeah, if you really want to think about it, it could be a negative charge on the right hand side, and that's why the arrows are pointing that way as well. All right, if you just want to mentally think about it that way. Okay, so an electron is placed in here. All right, so E minus. Well, what's going to happen? Well, we know that electrons, they love the positive side and they hate the negative side. So as a result, if you just throw an electron entering it from the left and you're making it move towards the right, well, the E field is going to cause it to slow down, right? Because the electron will want to move towards the left. So you would expect the acceleration to be negative when you calculate out your final answer for this thing here. Okay, it will decelerate, meaning that energy will be stored. It's kind of like I'm pulling on this and it's slowing down and coming to a stop. Okay, so I am storing work into this. Okay, let's go and calculate this away. First off, determine the change in electric potential energy. All right, change in electric potential energy acting on the electron. Okay, and when you're solving this problem over here, you just gotta think about carefully of what's happening into the system, as opposed to just blatantly shoving numbers in and hoping for your best answer. All right, so that's why you'll see that when we go through our calculations here, when I show you the formula, I'm gonna put plus minus sign because I need you to think logically what's happening here. Okay, once again, when you know the E field's moving towards the right, and this is a negative charge that's being placed into this E field. Probably better off drawing it like this. Okay, so it's a negative charge being placed into an E field. If you want to think about it, it's a plus sign on this side over here. The electron will be attracted towards the left, so as a result, the corresponding Fe will be negative. I don't know, minus VE. I don't know, just as a reminder. Okay, it will be negative. So that's why the corresponding work that's done on this, because it's the field is in the opposite direction of where the object's moving, this will be a negative answer. All right. So again, the negative answer is not based upon the charge or the E field, because the E field is a vector quantity at the end of the day. All right. Like this one over here is just telling us it's moving towards the right. What if it's pointing towards the left, then what sign will you use? Okay. So it has nothing to do with regards to the charge and the right, because it could have just been towards the east, let's say. All right. And that will mean nothing to you at that point there. Okay. So you really just got to think about, how the field is impacting that charge. Okay, so in this case over here with a negative charge, it's impacting in such a way that's going to decelerate. So it is going to perform negative work here. Oh, I have an animation here. There you go. Cute little animation. It's as if it was a negative charge on the right-hand side, and it's as if it was a positive charge on this side over here. Just to emphasize that this electron will travel and then slow down and slow down, and at some point come to a stop. That's all. All right, so the work done on this is equal to QED, and you'll notice that I don't have any minus signs inside because I want to define that the overall work will be negative. All right, so it's a charge of 1 electron. Remember that 1 electron has a charge of 1.602 times 10 to the negative 19 coulombs. If you had 2 electrons, then yeah, it would be double of that, 3.2 times 10 to the negative 19. If you had 3 electrons, then it will be at 4.8 times 10 to the negative 19 coulombs, and so on and so forth. All right, a theory that's been proven by Robert Millikan. He was the first person to discover that there was a such thing as a unit charge. So the charge of the smallest object, which today we know of as an electron. I think we're going to cover that in a future lesson, because I don't think we've covered it so far this year. No, we haven't. Okay, so we will cover that idea later on. But right now, again, it's just of 1 electron. That's why we're using this number here. The E field is already defined at 145 newtons per coulomb, and this charge moves a total of 3.1 meters. Did it come to a stop by 3.1 meters? We don't know yet. Okay, we just know it's traveled 3.1 meters. And what was the work done on this in this venture so far? So we sit down, we do all the calculations, and we get an answer of that. Okay, the E field, as I mentioned, did negative work because it's causing the electron to slow down. All right, so if you also remember from back in grade 11, by definition, or even in our previous unit, of energy, work by definition is equal to the change in energy. And in this case over here, we're looking at the change in kinetic energy, because we know that there was kinetic energy of 1.7 times 10 to the 7 meters per second, which we can calculate the amount of kinetic energy by doing 1/2 mass of the electron times v squared. So we already know how much energy it had initially. Okay, we can calculate it out, and we're just seeing, how much has this slowed this down by. Okay. Yeah, it doesn't really define whether they come to a stop or not. We just know that it has slowed down. Okay, so work by definition is the change in kinetic energy. You just have to simply sub in everything super carefully. Electrons, they do have this mass over here. Right, that's a known constant. It'll be given to you on a reference sheet, right, if you're curious about that. So that's a reference value will be given to you, and this is also another reference value that'll be given to you as well. All right, so it's really just taking the values, subbing them in, and slowly rearranging it and carefully solving it. And your final velocity, it'll give you a number at the end of the day. All right, in this case over here, it gave you a lower value. Okay, because you started off at 1.7 times 10 to the 7, and you dropped down to 1.1 times 10 to the 7. So in this case over here, it did cause it to slow down. All right, it did do negative work. On the other hand, if you're curious, if this was a positive charge, well, you can think of the E field as if, it's all pointing towards the right. So initially, the charge was positive, or the E field was positive in the first place. Maybe I'll draw it like this. So if you drop a positive charge in here, positive hates positive, it's going to run away faster. So it actually will accelerate. All right, so that will be a positive answer, and you'll have a value that will be greater than 1.7 in that case over there. Yeah, I do strongly recommend that you try out practice examples 2 and 3 on page 349 as well. Okay, a bit more definition. Okay, so we just covered electric potential energy. Again, use this as your hint. You're trying to find out energy at the end of the day. So what exactly is electric potential? It's a fancy word for a volt. That's all it means at the end of the day. Okay, electric potential is what is a volt. What exactly is a volt? If you remember grade 11, the formula at least, V is equal to E over Q. Some textbooks write it out this way. Others will write it down as E over Q, and others will even write down W. All right, it's either the work in moving the electron or the amount of energy that's stored in that charge. Okay, so work by definition is how much energy there is per charge, per coulomb, let's say, of charges. Okay, so that's what a volt is. Okay, volt is how much energy there is per quantity of charge. Okay, you can think about it in this picture over here. Okay, let's say that we have a nucleus of a proton. I'll say we have a proton. Okay, so we have a proton, and a proton provides E fields that radiate away from it. If you so happen to place an electron somewhere right over here, that electron, yes, will want to rush towards the proton. So there is stored energy in there. But that stored energy is based upon how many electrons you have, all right? Because if you have one electron, then it'll have that much energy. If you have two electrons, then you'll have double the amount. And that's why the volt by definition is how much energy there is per X number of electrons, which you may not know yet. And that's what all volt is, okay? Volt is how much energy there is per quantity of electrons. Okay, so if this formula is correct so far, then we can rearrange it, and I think that's on the next day's PowerPoint. Okay, we're going to take this formula and do a bit of rearranging. So make sure you leave some space in your notes because you're going to add more towards this for for tomorrow's PowerPoint. Okay, so this electron over here, we know that at some point it's going to race from that orbit to an orbit much closer to the positive charge, right? And that point over there, you've done work, all right? Or there's a change in energy. If it was a positive charge, on the other hand, it's going to move in the opposite direction. Okay, so what exactly is the potential difference then? Well, that's the amount of energy that it will either release when it moves from one state to the next, or if you force it from point A to point B, that's how much work that you've done in moving the charge from point A to point B. All right, your electromotive force, if you want to think about it that way. Okay. So that's the electric potential difference is then therefore your delta, okay, your change in voltage. So for that change in voltage, there needs to be a change in energy state, okay. So that's why the formula is just delta delta, okay, which if you want to expand it out, it's E final minus E I all over the same exact charge, okay. Amount of work required towards moving a charge from point A into point B. Do I have it animated? Yeah. Okay. That's electric potential difference. Just as an example, just so you can think about it, why do they call it potential difference? Part of it is because you need to measure the potential between two given points. All right. So I have a bunch of batteries on the screen, and let's say I want to measure the potential difference using something like this, a good old multimeter. Now, this is an analog multimeter, but you get the idea. Multimeters always have two leads. There's one lead that's red and another lead that's black, right? And then there's going to be a screen. It could be an analog screen like this one over here, or a digital LCD screen. And it'll give you a result based upon how you wire this up, all right? If you wire the black lead, let's say towards right over here, and the red lead, you bring it all the way over here, well, the potential difference between just that one cell over there is 1.5 volts. Okay, and if you remove this wire over here, it'll drop down to 0 because it's measuring between no two different points, right? You need to have a difference for it to measure a value. That's why multimeters have two leads. Okay, so if I connect this from here to over here, you can see that the potential drop between these three is 3 sets of 1.5, which works out to 4.5 volts. And if I still happen to stretch this lead all the way down here, then yeah, it's going to have a potential difference of 6.0 volts. Okay, it's just a reminder that potential difference is always measured between two reference points, right? Between point A and point B. That's your potential difference. I think there's one more terminology just to point out, and we've covered it back in grade 11, but let's just cover it one more time now, okay? The electron volt. And the electron volt, by definition, is how much work is required for an electron to move between plate A and plate B. Chances are plate A is negative and plate B is positive. All right, and it needs to move from point A to point B. Now, while it's moving there, the potential difference between these two plates is 1 volt. An electron has a charge of 1.602 times 10 to the negative 19. Okay, so 1 electron volt is equal to the 1 volt times 1 coulomb. And if a volt by definition is a joule per coulomb, then it works out mathematically to a value of this, 1.602 times 10 to the negative 19 joules. Okay, so even though by definition electron volt is the work required to make an electron move from point A to point B over a difference of 1 volt, at the end of the day, it is a measurement of energy. And you can see that this energy is insanely small. Okay, so electron volt is a measurement, not a voltage, it's a measurement of energy. Okay, it's a common mistake many students make. They think it's a volt. No. Volt, again, is how much energy there is per quantity of charge. Okay, an electron volt is how much energy there is. It's a really weird unit, but we need to use this unit in physics because sometimes we have massive measurements and sometimes we have tiny measurements. I mean, you can think about a ruler, which I do have one right over here. Okay, with regards to rulers, if you're doing really, really tiny measurements, you'll be measuring it in millimeters, right? If you want to, like, for example, find out, I don't know, the thickness of this rubber band, right? You'll be measuring it most likely in millimeters. If you're measuring something quite a bit larger, like, for example, I don't know how big, I don't know, my cell phone is because I just have this over here, you're more likely measured in centimeters. And, you know, for the height of me, you'd probably measure it in meters, and, you know, distance from where I am to wherever you're watching this from, you'll probably measure that in kilometers. All right, so these are differences of scale in the world of distance. All right, where sometimes you have, you know, a unit convention for large distances and a unit convention for small distances. Now, what works out better as an analogy for this is that crazy American system of distance. Right, where in large distances you'll measure it in miles, in shorter distances you'll measure it in yards, and in even shorter ones you'll measure it in feet, sorry, or 1 foot, and in smaller distances you'll measure it in inches and even in mils in electronics. All right, for very small distances, and this has everything to do with the American or imperial system of measurement. All right, and the reason why I'm showing you this with you is because the numbers are so crazy, and I can't remember what it is in miles. I think it's 5780 feet. All right, and there are 3 feet in a yard. 1 foot is 1 foot, and inches, well, there's 12 inches in 1 foot, so 1/12 of a foot if you really want to think about it that way. And a mil is 1,000th of an inch, so it'll be 1/12,000ths of a foot. And you can see that these numbers over here, they seem nonsensical, all right? And that's just the irony of the system, all right? Because they use different references on measuring distances back then, and as a consequence of all the madness, you can see that these numbers are just really, really weird, all right? 1 foot. Okay, there's 12 inches in a foot and 5,780 feet in a mile. At least I think that's the answer. You know, just do 660, which is the length of an average farm field, multiplied by 8 times that the mule has to walk back and forth and plowing it, and you'll get to the answer. I hope it's 5780. That's how I usually memorize that thing. And the reason why I'm giving you this crazy thing over here is because when you're measuring the world of energy, we wish it was as clean as the metric system, but it's not as clean as the metric system. Okay, in the world of energy, if we ever need to measure very big measurements, we're not going to measure, well, you can measure in megajoules, but instead they measure it in kilowatt hours. All right, oops, capital W. Okay, so big quantities of energy, you measure it in kilowatt hours. Don't be confused. All right, hours is not measurement of time. It's when you finish measuring this calculation over here, that translates into 3.6 million joules. Okay, so big energy is measured in kilowatt hours, and unfortunately, it's not a clean metric conversion. In smaller measurements of energy, you'll just measure it in joules. 1 joule is equal to 1 joule. And in very tiny measurements, again, it's not a metric system, you measure it in electron volts. So 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. It's almost as synonymous as, you know, measuring things in inches and in miles. All right, it's just this weird, crazy conversion between them all. Inches, even mils is a better example. All right, because it's a big unit scale difference. Okay, so whenever you're dealing with big quantities of energy, you'll measure it in kilowatt hours. Whenever you're dealing with very tiny quantities of energy, you'll measure in electron volts. And in grade 11, you might have remembered that sometimes electron volt is too small, so we'll cover it in mega electron volts, which then will be 1.602 times 10 to the negative 13 coulombs, I believe. Add 6 to negative 19. Yeah, that's the right answer. Okay, so again, I want to go through this just as a review because we'll need to cover an electron volt in tomorrow's lesson. All right, so tonight's homework, yes, it is to do a lot of reading. So please, on top of doing the homework questions, read ahead because you need to comfortably understand what these units mean so that we can glue all together to solve these more elaborate problems. Okay, and that's it for today's adventure. I'll catch you tomorrow.